left off talking about the model of the atom that was brought to us by J.J. Thomson, the idea of the Plum pudding model, that the atom was actually a sphere of positive charge and scattered throughout were these negatively charged electrons that were really, really tiny. This idea kind of revolutionized the atom because up until then it was just a solid sphere. And new inventions and new discoveries in nuclear physics led to people wanting to know more about how the atom worked. They had a realization that if they understood how the base components of all matter actually worked, then we would have a better understanding of how the universe worked and could actually start creating materials and equipment and things like that that manipulate those properties of the atoms for our own benefit. And so, just a few years after J.J. Thomson made the discovery of the electron, came another physicist to do some experiments about the atom. This person was Ernest Rutherford. And Ernest Rutherford did these tests actually after he had already won a Nobel Prize in physics. And so, what he wanted to do was have a better understanding of how the atom actually worked. In order to do this, he actually set up what is probably one of my favorite experiments of all time. So we're going to take a look at this experiment and take a look at the hypothesis that he created and why this was such a great experiment. So this is what he did. He set up something called the gold foil experiment. To understand this, you need to know that he was taking a box with a small slit in the front that was shooting out radioactive particles called alpha particles. Now, nobody really knew what an alpha particle was, but they knew they were really, really, really tiny. He used this box to actually shoot alpha rays, and what he then did is place a very, very thin film of gold foil in front of the alpha rays. And so think like gold leaf, like you're making a fancy cupcake and you're going to decorate it with your gold leaf. That's basically what he put in front. And then around it, he put a fluorescent detector that would actually detect when alpha particles hit it and where they hit. So, to understand this experiment, we need to understand his hypothesis. And the idea was that if this was the structure of the atom based on the Plum pudding model, the alpha rays, which are the black arrows here, should actually just pass right through this gold foil. I think it's also important to recognize that there was another possibility that he thought. If the ball of positive charge was actually solid, they would have fully bounced off and gone entirely different directions. So really, those were kind of the two ideas. It either goes straight through to the other side, or they bounce completely off and go different directions. Here's what he found. He actually found that the majority of the particles went through to the other side undisturbed. Basically, they were traveling through the gold foil, and keep in mind, not ripping the gold foil, like actually just passing through it, like a ghost through a wall, and then they hit the detector on the opposite side. But periodically, some of these alpha particles would bounce and go an entirely different direction. If you think about what those results actually mean, it means that the atom isn't entirely able to go through, the alpha particles can't entirely go through the atom, but they're not entirely bouncing off. Some are able to get through, but a very small percentage are actually bouncing off. What that means is the solid part of the atom is actually pretty tiny, and the rest of the atom is mostly empty. And that leads us to his new model of the atom. You see, this was the Plum pudding model. The Plum pudding model, we already discussed, was the hypothesis. But Ernest Rutherford discovered that there had to be a nucleus, a highly positively charged, dense center inside of the middle of the atom. The electrons were then scattered around the outside of that atom. And his results are because the electrons passed through, the alpha particles passed through, not interacting with the electrons, and then periodically they would collide with the nucleus. When that happened, they would bounce off in a different direction and collide with a different spot on the detector. This is what we ended up getting out of it. It is Rutherford's new model of the atom. And I know it doesn't look like much, but it basically explains what it needed to. There's a nucleus in the center, and that nucleus is positively charged. There's electrons around the outside, and they're negatively charged. They're just kind of scattered, and all of this other stuff in between is empty space. It's kind of crazy to think about this, but the amount of empty space in an atom makes up roughly 99.9% of the volume of an atom. That means almost the entire atom is made of nothing, like literally nothing, like no matter in that atom, but they're so solid that we actually can't go through them. And so this was a huge revolutionary change in the way that we started to think about atoms, having this really, really dense nucleus and these negatively charged electrons around the outside. Now, there was a problem though with Rutherford's model. You see, Rutherford's model didn't really account for some of the things that they noticed about atoms. And so one of the big problems is if you have this positively charged nucleus and this negatively charged electron, what's actually stopping the two from just crashing and colliding together? And they also noticed that certain atoms were always giving off the same amount and types of energy. And Rutherford's model really didn't explain that. So it came up to another physicist that we'll see in our next video that actually finally was able to come up with a more complete picture of the atom. So thanks for watching, and I'll see you next time.